Hello everyone, welcome to Academic Coordinates. In this video, I'll be deriving the Bernoulli's equation for an ideal flow. So by an ideal flow, I mean it's a non-viscous flow. In other words, the viscosity equals to 0. And, it's an incompressible flow, right? So the density is constant, right? I did say, obviously, that it's a non-ideal flow. So everybody, welcome to Fluid Mechanics. In order for us to derive the Bernoulli's equation, we're going to start with Euler's equation of motion, which equals to the material derivative, the body force field minus 1 over density delta P, right? Then this, guys, is Euler's equation of motion. All right. So to continue from here, we're going to express the material derivative in another form. So that's the partial derivative over here plus v dot cross v. So this is this part. It still equals to the body force field minus 1 over the density delta P. All right. So at this point in time, you would be given identities of vector field, right? And it is these identities that are going to assist us to find, or to express this portion of an equation in another form. So the identity that we're going to use is the del of v dot v. This is the dot product, guys. You are used to that. V dot del over here. I transform this equation I'm writing. You are seeing which part are we going to make the subject of the formula. So V cross del cross V over here. Okay. So in order for us to make this portion the subject of the formula, which is this part in this equation, it's going to be v dot del v is equals to something, right? So we're going to divide by 2 everything and take this guy, the other side of the equal sign. So it's going to be 1 over 2 del v dot v minus now this portion, which is going to be v cross del cross v. Okay, so now we are going to substitute this portion into this equation right here, So we continue there, delta v divided by, the partial derivative here, plus, actually supposed to write that in white, eh? Okay, but it's fine. We are substituting here now, right? Then plus 1 over 2 delta v dot v, this part, it's v squared, right? Trust that you guys can appreciate that. Minus v cross del cross v, right? So now I've substituted this whole portion with this right here. Then that still equals to the body force field minus 1 over the density, then delta P over here. Okay, guys. So now we're going to simplify this equation even further. Let me actually go back to the white I was using. We're going to simplify the equation even further. We still have our partial derivative here. Plus, let's write this equation in this form. V squared over 2, right? And then let's take this part of the equation on the other side of the equal sign. And then here, we can just bring minus the body force field, right? and then plus 1 over the density del of P. This equals to V cross del cross V. Okay, so there is another parameter that we know from just from this equation. This part equals, this part is called vorticity, right? So we can substitute that as well and make our lives even much more easier. Okay, so the partial derivative plus v squared over 2 minus f of b plus 1 over the density del of p. This equals to v cross the vorticity, right? Okay, cool, guys. Let us continue. At this point in time, having an ideal flow, right? It will be complex, obviously, to solve for pressure, velocity and vorticity, and hence because would need to know all of these things at each and every point in this ideal fluid. So the solution to that is that we need to rewrite this equation and make it applicable, right, along a streamline instead, and so with that being said, let us make our assumptions first, right? And remember, guys, we are deriving Bernoulli's equation. We need to make some assumptions. Okay, so assumption number 1 that you're going to make is that this flow is vortex free, right? So, or the vorticity, in other words, is going to equals to 0. This is the vorticity, so it is going to equals to 0. By this flow being vortex free, it means that the vorticity, which is del cross V, this should equals to 0, right? Okay, so because of that, there exists a velocity potential. The velocity potential exists. Velocity potential, it exists such that the velocity will be linked in this manner, right? Because the vorticity equals to 0. And also because now, as you can look, guys, on the right-hand side of the equation, if this is 0, right, it simply means that V cross the vorticity, that is 0, we are still going to get a 0 over there, right? Since our vorticity equals to 0. And so our equation is going to be simplified in this case, right? The second assumption that we need to make, that this is a steady flow. So for a steady flow, it is time independent. So the velocity change in this flow is not affected by time. It's not dependent on time, So what does that mean for our equation? This portion of the equation, the partial derivative over there, will equals to 0 because we assumed steady flow, And the third assumption that you're going to make is that FB is conservative. Right? Obviously, this is the body force field. So, because of that, now, there exists a time-independent scalar field, omega, right? There exists a time-independent scalar field omega. And also just take note, guys, that this is the body force field, right, for which we only consider gravity, you know. Okay, so now we consider there is a time-dependent scalar field omega such that our FB equals to minus del of omega, you know. And then this implies that del cross del of the omega equals to 0. And then obviously if we equate the z components of this result here, obviously the ones that don't equal to 0, right, we are going to get that this is the case, partial derivative in terms of z. Okay, and obviously here we can just divide there and also a negative. So we're going to get g equals to the partial derivative over there in terms of z. So in order for us to solve here for omega, we need to integrate, you know what I'm saying? So we are going to integrate here. Okay, that was not good. Let's see. That's not okay. All right. So we're going to integrate here. G delta z. Okay. So omega now equals to gz, right? Or you can write this as gh. You know what I'm saying? Okay. So even now our equation is being simplified even further, you know? And so let us just take this equation that we have here, and having assumed the following these three conditions here, let us see as to what it shrinks to, you know? And just remember that our equation was in this form. All right, so that was plus 1 over 2 v squared. Okay, no, just got carried away there. So that was plus 1 over 2 cv squared del over there minus fb plus 1 over p. Sorry, that's density, by the way, which is different from this one. And then v cross the vorticity over there. Okay, so from the assumptions that we have made, let's start with the first term over here. This term equals to 0 because we assumed a steady flow, right? So because as you can take note on the first assumption actually, that there exists a velocity potential and hence v equals to that over there. So we've got this place delta t. Okay, this remains the same, minus fb plus 1 over the density. I think I'm taking a long dry here. That's the vorticity. So this portion here equals to 0. Then this one remains the same, v squared over 2. And then the body force field now, fb, is, we've got it over here, minus del of omega, right? So minus times a minus is going to be positive, plus del of omega there. And then we continue, it's 1 over the density del of p. So as you recall from the first assumption that we assumed a vortex free flow, right? And so the vorticity equals to 0. And so if we cross that 0 with the velocity there, we're going to get a 0, right? Okay, so now at this point, because of we need to arrive at our Bernoulli's equation, we are going to dot each and every term, right, with the displacement vector. So at this point, we are going to dot each term with the displacement vector, right? And we're going to integrate. All right. So let us do that right here. Right, then we've got L of v squared over 2 plus this guy over here plus, you see everything still falls into line, density delta p. So we're going to dot this with dr is equals to, it's going to equals to 0 now because we are going to dot two vectors, you know. Okay, then guys, as we continue here, going to get to a point where as we are dotting this thing and integrating, plus d of omega over there, dp for the density, that equals to 0. Okay, so finding the integral here, and you know, we're going to get v squared over 2 at this point. And then for this section of the work, we are going to get our omega. And then even the integral here, this point, this is going to equals to an integration constant, right? So at this point, guys, remember that we assumed this is an ideal flow. So for an incompressible flow, the density is constant. Because of that, this part of the equation, it's going to be 1 over the density and then dp. Then we're going to get p over our density over there, because this is constant, you know, obviously plus the integration constant. Okay, so what does our equation boils down to? So we've got v squared over 2 plus omega plus p over the density, pressure there over density. Then that's the integration constant, right? So voila, we have arrived at the Bernoulli's equation. And then omega, we actually solve for omega on the third assumption. Omega is gz, or you can call it gh, whichever one is going to help you to sleep at night, right? That's gz plus p over the density. That equals to a constant. So the sum of these three are going to give you a constant, and that is Bernoulli's equation. All right, guys, stay blessed. Enjoy the rest of your day. If there is any uncertainties, let me know. And yes, thank you.